Hey guys, it's Chili here. Welcome back to Advanced C++ Tutorial 3, Part 2. In Part 1, I introduced you guys to the dot product, taught you how to use it, how to visualize it, and then we used the dot product to derive a formula for a rigid body collision to calculate the rebound velocity after a collision. In this tutorial, we are going to create a little simulation, a little physics simulation, and implement that formula using the dot product. Alright, me hearties, let's take that vector formula that we derived and actually write some code with it. So, first thing we're going to need is we're going to need a plank and we're going to need a ball, because that's what we're going to be, doing our simulation about. So where is my stuff here? Well, the first thing I did was I removed the stuff that doesn't apply to this tutorial from our code base. So I removed, all this random generation bullshit, and I removed the Starbro class, and yeah, all this stuff here, it's gone. It's gone now. Goodbye. And the next thing I did was I added a beautiful plank. So plank boy looks like this. You press up, it tilts in the upwards direction. You press down, tilts down like this. It's got a fixed range where it can move within, and it's all good. You can see here, I'm not actually rotating the plank. I'm only moving this point here. Well, this point here stays fixed. I'm moving this point up and down, and then I'm generating the other 2 points that are just offset in the y direction, like this. So it's not a rotation. You'll see what I'm doing in a second here. So what I do is I make plank inherit from entity, so I can get the benefit of all the stuff we've built up about entity and the drawable system. So what it's doing is it is storing, well, obviously because it's an entity, it's storing its own position. That's in the base class. It's also storing some information. It's storing the free point in model space. Now the free point is the point on the left, the one that can move up and down. And it also stores the minimum and maximum y value of that free point in model space, and it stores the fatness of the plank. And so what we do is when we construct this, we give it the x of the free point in world space and the minimum y and maximum y in world space, and the anchor point is the right point, again in world space. And it uses that to derive the x and the y things for the model in model space. And the other point, the anchor point, you might be wondering, where does it store that? It doesn't need to, because the anchor point is going to be set as the origin in model space. So you don't have to store that. You just have to store the position of the free point in model space. And what it does is it stores this information about the model space point. And when it is time to draw this mother, what it actually does is it generates the model dynamically. So this is the anchor point, it's just at 0, 0. And then the free point, the one that moves, pushes that back. And then it pushes back the free point offset up by the fatness. And then it pushes back the anchor point offset up by fatness. You got 4 points, and you draw a quad. It's going to be a parallelogram. And so yeah, I added a function set model to entity to allow us to modify the model from the child class. And then in game.cpp we generate the plank, and yeah, when you press down and up, moves the plank's y up and down by 2 per second, I guess, or 2 per frame. And drawing, you get the drawable, you draw the plank. Not too complicated. All right, now the next thing that we needed was a ball, and I'm drawing it. Here's the ball. It's just going to be a thin line circle. But I'm drawing it in a little interesting manner, because we want to put it into our transformation system. It would be nice if we could draw it with a polyline, and I can generate a polyline circle using star make if I just set the inner and the outer radiuses to be the same. So that's what I do, and it's good times. And again, it has a velocity, it moves in time, so we give it a velocity, and we also remember its radius, just like we did with the Starbro, because that's going to be useful information when we want to detect our collision. And there you go, you've got your ball. Game.cpp, it's generated here, it's updated here, and it's drawn down here. Now the last thing I did was I made the ball so so that it generates in a range of directions like this. You get different directions every time it generates. And I also made it so that when the ball gets too far away, it will be cleaned out of the container of balls. And there you go. We've got our setup now. We're ready to start implementing the rebound physics. The code for that, by the way, here, I've got the spawn point, and it just, it wraps around some random number generation stuff and some parameters here. And then on update, it will, spawn a ball when the time is right. And game.cpp is just added into here. I've got a vector of balls, and then in here, we update all the balls in a loop. We draw all the balls in a loop. It's all good. For the ball cleaning, I just added a little constant here, max ball distance. That's the maximum distance from the origin, I guess. And down here, I just do a little remove if erase bullshit down here. Not a big deal. All right, let's get actually started here. So saying this is our plank, if we got a ball, how do we detect whether it is colliding or not? Well, if you've done the homework for tutorial 1, then you should already know this. You should already be able to figure it out. The answer is we want to see if this circle intersects with the line. And how do you do that? Well, we check to see whether the distance between the center of the circle and the line is less than the radius or greater than the radius. If the distance is greater than the radius, then we know that the ball isn't colliding. If it's less than the radius, then it must be colliding, i.e. overlapping. And then we can handle our collision using this guy here. So, distance between a point and a line, that has an equation for it, has a formula, and that formula generally requires us to have the line in the form of ax plus by plus c equals 0. Now, one thing you might be wondering is it okay for us to do the calculation between the distance of the point and the line? Our paddle, or our plank, is actually the line segment, so shouldn't we test to see whether it's past the ends? The answer is no, because I made my ball distribution of trajectories so that it will always pass through the paddle. So we don't actually have to check to see if we are going to go past the end of the paddle or not. That isn't going to be an issue for us. In general, though, you would have to do extra work for that. So essentially, I want to calculate the distance between the point and the line based on 2 points on the line and the point of interest. So we'll call this one P0, P1, and Q. This is just a general math formula. So what I'm going to do, I'm going to create a general header called chili math. It's going to hold some, basic general math functions. I often do this. So we're going to include cmath. We're going to include vec2. Let's create a function, and we'll make it templated. So type name t distance point line, and we are going to take a vec2. We'll make this reference just to be safe. We'll call this p0, p1, and q. And since this is in a header, that's okay. It's template, so we don't have to make it inline. But if you put a free function in a header, you got to write inline in front of it. But in this case, not so necessary. All right, so this is vec2. This is actually not what we want. We want to use the templated type. So that'll look like this. Just a small note: you really shouldn't start your types with underbar. It's not a good thing to do, but I've already started, so it's okay. It's not hurting anything right now. But in general, probably don't want to do this. Do as chili say, not as chili do. Anyways, so how do we figure this out? Well, we've got to be able to take general points and calculate A, B, and C. Now, I could do this by, writing it out algebraically and with all the symbols and then working it into an expression, or I could literally just Google ABC from 2 points and the answer's right there. So the answer is A is equal to YA minus YB, XA minus XB. Yeah, so A and B are just our 0 and 1 points. And this will give us the values of all the coefficients. And that's a beautiful thing, because that means I have to do less work. And that's going to look something like this. And then we just got to do the distance between a point and a line. And that's this guy right here. And that's going to look something like this. Notice that I defined a little template function square. That just returns the square of the parameter here. So there's our distance point to line. Hopefully I typed it out all correctly. But if I made a mistake, I'm sure we'll find out soon enough. All right, now in the plank, we can get a vector in the direction of the surface, but we want to get 2 points on the line of the surface. So what I'm going to do is just go auto get points const, and we're just going to return a std pair. So we'll get the position, and then we'll return std make pair position, which is going to be anchor point, and then position plus free point is going to be the position in world space of the free point. Now, when we have a collision, we want something to happen. So let's include sound.h, and let's. What I did is I pulled in good old friend. Where is he? Sound. Like this, and then we put a wide string, and what was the name? I believe it was sounds double backslash arcpad.wave. So that's going to be our sound. We're going to play that when we detect a collision. Maybe I'll rename that the collide sound, just for there to be no confusion. So what we want to do, we got to include chili math. Let's not get ahead of ourselves here. So we include that bad boy in there, and then we want to do if distance point line. Well, let's go const auto plank points is equal to plank dot get points. So far so good? Yeah. Distance to point line plank points dot first plank, that's not how you spell that, plank points dot second, and the ball, there's multiple balls. That's a problem. We got to loop. We need to loop. Well, I mean, we're already looping, right? Why don't we just put this bad boy into here? Second ball dot get pause. Position of the ball is the center of the ball. That's what a center be at. So I'm not quite done here. So if this distance is less than ball dot get radius, then we have a collision. And what do we do with our collision? We do collide sound dot play. Let's see if this works. All right, it is not working. So, time to see what's going wrong. All right, time to debug some stuff. So debug, yeah, go. We want to pause it when it is right when it's colliding. Stop. There we go. I believe that was a good one. So now we are in break mode. Let's go to game.cpp. Let's set a breakpoint here. All right, now we're going to have multiple... That sucks. We're going to have multiple balls, and we only want to break on the one that... All right. So we're going to set the breakpoint here at the beginning of update model. We're going to continue. Here we are. All right. So now we should have one ball that is colliding, the rest are not, but I'm not sure which one is which. So how do we handle this conundrum? Well, let's just step. Can we step? Yeah, here we go. Step over. There it is. All right. So right now we notice that our ball has a radius of -4 billion or so, which is probably not what we're looking for. I'm guessing that's not an accurate representation of the simulation. So let's go into ball.h and let's notice that we didn't actually set the radius. So let's do that. And let's see if that fixes our problems. I'll run in debug again. Ooh. Okay, now it's working. So let's just bring this up here. Now you'll notice we're getting a whole bunch of them here. I don't know if you can hear this. It's kind of cacophonous. And that's because every frame in which it is intersecting that line, it is going to play the sound. It's going to play the sound for a short duration. It's going to play the sound every frame. It's going to sound like garbage. But it works. We can detect a collision. Now all we've got to do is handle the collision appropriately. So again, looking at our wall of math, we need W. We can get that by calling a function on the plank. We can V, which we call a function on the ball. And not much else, except we need to be able to do the dot product, which we haven't implemented yet. So let's implement the dot product. Now the dot product, as you may remember, product of two vectors returns a scalar. So we want T here. And I do the dot product as the multiplication operator overloaded for two vectors. Some people don't like that. They like a different thing. They like to call it maybe a function dot. That's fine too, but that's not my style. So const underscore vec2. You might pass it by value. I'm not quite sure which one is going to be more efficient in most cases, but I really don't care either way. Right hand side like that. Const, of course. Don't forget your constness. And then we're going to return x times right hand side x plus y times right hand side y. And there you go. Dot product defined. So the const vec2 w is equal to plank dot get plank surface vector. Const vec2 v is equal to ball dot get velocity. Ball dot set velocity. And again, 2 times v dot w times w minus v. All right, so we probably want to put this w out in front because the way we've defined our operations, we don't have an operation for scalar times vector, only vector times scalar. So we will do w times v times w times 2.0f minus v. Do that. And there you go, all that work. But it's actually a pretty clean little bit of code here once you code it all up. Nice and clean, simple. Now, what the hell, let's play the sound too. It'll be fun. All right, let's go. No bugs whatsoever. It's gonna work perfect first try. Okay, well, I'm not sure that's exactly what we were hoping for. Doesn't seem like it. It occurs to me that w vector is p1 minus p0, but w hat is the normalization of that. And if we don't normalize it, it is going to be a very big velocity coming out, and it's probably just going to fly away in one frame, which would account for the disappearance. So what we want to do, very simple fix, get plank surface vector dot get normalized. And there you go. Beautiful. Lovely. I'm loving it. Let's see what it goes this way. Oh yeah. Are you guys checking this out? We have got some pretty decent physics going on here. I do indeed love this. Alright, now it's time for the homework. We've got a nice system here. Looks like it's working pretty cool. Let's try something here. We got some, rebounding. It's going off good. I love it. What the hell is going on here? Oh my god. Okay, well, might not be perfect yet. So, I could tell you what the problem is, and I could show you the solution, but I think it's more interesting to leave that as a little homework assignment. So, your assignment is to figure out, what's the problem, what are the conditions that cause the problem, and how would you go about solving the problem. A little bit of debugging homework for you. Good stuff. Well, that's going to about do it for today. I just want to say, don't worry if you can't yourself, fluently manipulate vectors and geometry diagrams and derive these kind of expressions. It doesn't come all at once. It takes some time, so don't get down on yourself, but do try and stretch these muscles when you can. If you feel you're lacking a little bit, maybe look up some assignments, some videos and exercises you can do with vectors to help expand your mind a little bit. See, the dot product turns vectors from cool dudes into motherfucking superheroes, and we're going to see more of them, especially in 3D fundamentals. Next video is going to be rotation to complete our repertoire of essential transforms, and the dot product is going to play a crucial role in one of the derivations that I will show you for the rotation formula. As always, thanks for watching. I hope you enjoyed the video. If you did, please click the like button, it helps a lot, and I will see you soon with some more advanced C++.